Hello and welcome to the second of the lectures in this fourth week under the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In the last lecture, we saw what fuzzy implications are. We generalized it to a particular axiomatic definition. We have seen some examples, in fact, basic fuzzy implications, what we call them as those 9 important fuzzy implications. And we've also seen some geometric perspectives of it. In this lecture, we will look at some desirable properties that we would expect a fuzzy implication to have. As was told, we saw a generalization of properties from the classical implication to that of fuzzy implication. And that's how we have come up with an axiomatic definition of a fuzzy implication. We also saw some geometric perspectives. In this lecture, we would like to elucidate some desirable properties of fuzzy implication. Of course, continuity is one of them. We would also see how to get negations from fuzzy implications. And once you have negation, we could also discuss contraposition of a fuzzy implication. Most importantly, we would look at 3 or 4 particular almost algebraic operations that you could call that of neutrality, ordering principle, identity, and exchange principle. Let's recall what a fuzzy implication is. We have looked at the truth table of a classical implication, and from here we said a function I from 0, 1 square to 0, 1 is called a fuzzy implication if it is decreasing in the first variable, increasing in the second variable, and satisfies these boundary conditions. And we also said that we will denote the set of all fuzzy implications using this symbol script. We tried to decode the axioms in a geometric way. Visually, how do they look like? We saw that the boundary conditions translate as these points on the 4 vertices of the unit square, and we are looking at decreasing along the first variable and increasing along the second variable. And we have also seen, using these boundary conditions, what we get is on the left boundary and the top boundary of this unit square, we want that the fuzzy implication should actually take the value 1. Well, now we have seen a few examples. Quickly to recall, these are the smallest and the largest fuzzy implications, and this is the Gödel implication on the left and the Reichenbach implication on the right, the Gauguin implication on the left and the Ukashevich implication on the right. Now let's look at some desirable properties. In the previous lecture, we had mentioned that in the axiomatic definition of a fuzzy implication, we have not asked for any algebraic properties, just the boundary condition and some monotonicity properties, which you could look at as some order theoretic properties. But it doesn't mean that a fuzzy implication is bereft of these algebraic properties. Let's look at a few of them. First of them is the neutrality property. Let's look at the classical implication truth table. Now, when you look at this truth table, it appears that when the first variable takes the value 1, then the overall truth value of the implication is essentially the value taken by the truth, the consequent q, the variable q, what happens at the second variable. So it appears that 1 plays the role of a left neutral element, and this has been captured as the left neutrality property, and typically it is also shortened to just the neutrality property. We say a fuzzy implication I has this neutrality property if I of 1 comma y is y for every y in the unit interval 0. Now let's look at some of the examples that we have seen, including basic fuzzy implications, whether they possess this property. Clearly, when you see here, this is the smallest, this is the largest fuzzy implication, they do not have this neutrality property. So now geometrically, visually, where do we look for this? So that is at x is equal to 1, we want that as y increases, that I of 1 comma y should be y. That means we are looking at the right boundary. We know that the left boundary is 1 and the top boundary is 1. Now we have two more boundaries. So the neutrality property specifies what happens at the right boundary. So it says that I of 1 comma y, if it is y, then we say that the implication satisfies this neutrality property. We see clearly here that neither of these implications satisfies the neutrality property. If we take the Gödel implication, then we see that at x is equal to 1, it is actually the identity function. That is, I of 1 comma y is y, hence it satisfies the neutrality property. So geometrically, what we are looking at this boundary, the right boundary, is that it should take the identity function. And we see the same for Reichenbach implication also. This is true also for the Gauguin implication and the Łukasiewicz implication. If you look at the Rescher implication, it is no more true, whereas for the Fodor implication, again, it is true. Now finally, for the Jaeger and Weber implication, for both of them, it is actually true. If you recall, we got the Weber implication from the largest implication I1. One way to look at it look at Weber implication as if it is being obtained from the largest implication I1 by just redrawing the values at the right boundary, which is at x is equal to 1. This is the Klein-Dienz implication. Clearly, it also satisfies neutrality property. But let's not go away with the feeling that we are only going to talk about I of 1 comma y being equal to y, but there are also a lot of implications where I of 1 comma y could be some function of y, continuous function of y, as in this case of I of 1 comma y being equal to y squared. So this is again a fuzzy implication. You will see it's a slight modification of the Klein-Dienz implication. So why we have y squared. We will see how this formula has been obtained. We will see that it's just a special case of particular way of constructing fuzzy implications in the very next lecture. So you see here, I of 1 comma y is actually y squared. So this right boundary here, it's not the identity function. So we also have implications of this type, not just that here it is 0 or some constant function. Okay, so this is what is a neutrality property. Now, let us begin by recalling what a fuzzy negation is. We know it's a unary function from 0, 1 to 0, 1, such that n of 0 is 1 and n of 1 is 0, and it is a decreasing function. We could have different classes of fuzzy negations, the involutive ones, which we have also seen earlier. N of x is x. It could be continuous, it could be strictly decreasing, it could be continuous but not strictly decreasing, it could be strictly decreasing but not continuous. We have seen examples of all these kinds. Now, why talk about fuzzy negation here? Let's look at the truth table of the classical implication. When you fix the second variable to be 0, it appears the overall truth value of the conditional P implies Q is nothing but the inverted truth value of that of P. So when Q is 0, the implication acts as if it's an inverter. So 0 implies 0 is 1 and 1 implies 0 is 0. Taking Q from this, we could look at what happens to implications when you fix the second variable to 0. That is when y is equal to 0. Now let's look at the plots of some fuzzy implications. This is the Gödel implication. Now when you look at y is equal to 0, that is essentially the bottom boundary, you see that at 0 it is 1 and the rest of the places it is 0. And in the case of Łukasiewicz implication, which is on the right, you see that there is actually a continuous graph here, linearly falling from 1 to 0. In the case of Fodor implication, once again, when you look at the bottom boundary, it is a continuous function. And this is a function which is essentially a modified form of Łukasiewicz implication. And here again, you see that in the bottom boundary, the graph of the implication is continuous, but of course, clearly it is not strictly decreasing. But we always see that these are decreasing functions. Taking Q from here, we could define, given an implication I, another auxiliary function Nn like this. Na of x is I of x comma 0. So essentially this is a partial function where we fix y to be equal to 0. Now clearly, from the definition of fuzzy implication itself, we can see that Na of 0 is 1 and Na of 1 is 0, and similarly it's a decreasing function. This function, which is a negation, is called the natural negation of an implication. Let's look at some examples of fuzzy negations. So this is the classical negation 1 minus x, which we denote by NC. And if you look at this, this is essentially the smallest negation that you could have. For example, if you look at this formula, what it says is, when you look at 0, 1, so then at 0 it is 1, and everywhere else it is 0. So this is your smallest negation. And if you look at the next one, NB2, this is the largest negation. At 0, 1, at 1 it is 0, everywhere else it is 1. So this is 0 here, it is 1 here at 0, and everywhere else it is 0. So this is ND2, which is the largest negation. And we could also have all kinds of other fuzzy negations, but let's just look at NP of x, which is 1 minus x squared. Clearly we have this ordering here, 1 minus x is smaller than 1 minus x squared. Now let's look at the plots of this basic fuzzy implication that we have and see what is the kind of natural negation that they have. Clearly for the smallest negation, at 0 it is 1, everywhere else it is 0, which means the corresponding natural negation is actually ND1. And in the case of the largest fuzzy implication, everywhere it is 1 for the natural negation except at 1, which is 0. So this is the largest fuzzy negation. And for the Gödel negation, as you can see, the bottom boundary is almost right here at 0, and only at 0 it is 1, so it gives you the smallest negation. Often this is also called the Gödel negation because it's being obtained as natural negation of the Gödel implication, which, as we will see later on, is a very important implication, fuzzy implication. In the case of Reichenbach implication, what we see is actually this is the classical negation 1 minus x. This can also be seen because what we are looking at is fixing y is equal to 0. When you put y is equal to 0, it is essentially 1 minus x. Similarly, for the Gauguin implication, we get the natural negation to be the smallest one, and for the Lukasiewicz implication, it turns out to be 1 minus x. For the Rescher, once again, it is the smallest negation, fuzzy negation, and for the Fodor, it is 1 minus x. Jager, it is again the smallest negation, and for Weber, it is the largest negation. This is obvious because we have seen that Weber can be obtained from the largest fuzzy implication just by V2 and the right boundary. As was seen, we don't always need to have one of these, either constant negation or the smallest or the largest of 1 minus x. We could also have the NP of x, which is 1 minus x squared negation. Okay, so far we have seen what happens at the left or top boundary, which is all the fuzzy implication is always 1. On the right boundary, we insisted that it should be identity function, which means the implication has neutrality property. And at the bottom boundary, we looked at it and saw that it was a decreasing function because as x increases, it decreases, and we saw that it is actually giving us a negation there. Now, we could also concentrate on the plots and see where it actually attains the maximum value, which is that of 1. So for the smallest fuzzy implication, we know that it attains the maximum value 1 only at the left and top boundary. Whereas for the largest one, it is almost everywhere it is 1, except at the point 1, 0. But now, when you start looking at some of the other implications, let's restrict ourselves only to the basic fuzzy implication. So an interesting pattern appears. For instance, it is 1 only above this main diagonal. This is x is equal to y, and not anywhere else. Whereas this, again, it is 1 for the Reichenbach, it is 1 only on the left and top boundaries, nowhere else. Wherever it's essentially required to be 1, only there it is 1 and nowhere else. When it comes to Gauguin and Lukasiewicz, once again, above the diagonal, they are 1, but outside of it, below that, it is not taking the value 1. If you actually look at this, it gives us a nice, interesting idea. For this, let's go back to the classical implication truth table. You see here, when P is actually equal to Q, then the overall truth value is actually 1. We could abstract this as a nice property where we say that I of xx is 1. Remember, in the case of T norms, we talked about idempotence, where T of xx is x, whereas here, going by the examples that we have, and also from the classical implication truth table, we see that a good way, perhaps a natural way of abstracting this property is as I of xx is 1, and this is what is called the identity principle. So essentially we are saying x implies x should be always true, more like a tautology. That's what they call in classical logic. But we also have something more. We see that here, when we have that when P is less than or equal to Q, once again P implies Q is 1. And this is abstracted as the ordering property, where whenever x is less than or equal to y, then I of xy is 1. Not one way, actually both ways. It's an if and only if condition. We say x is less than or equal to y if and only if I of xy is equal to 1. Now, this ordering property is extremely important, especially in formal logic terms, in proving results. Perhaps we'll touch upon this lightly in this setting when we look at conditionals or implications as being related to subsethood in classical set theoretic terms. And at that point of time, we'll make a mention about this property, how it could also be seen or interpreted. For the moment, let's abstract it from both the truth table and also from the geometry of fuzzy implication that we have seen. So an implication is said to have the identity property if I of xx is 1, and it is said to have the ordering property if whenever x less than or equal to y, then I of xy is 1, and on converse, I of xy is 1 if only if x is less than or equal to y. Let's look at some basic fuzzy implication and see whether they satisfy this ordering principle. As you can see in the geometry, Rescher implication satisfies this ordering property, and the moment you see that ordering property, which is OP, we'll abbreviate as OP, if it satisfies OP, then it also satisfies IP, which is the identity principle, because at this point, when x is equal to y, ordering property reduces to that of the identity principle. So OP implies IP, but clearly IP does not imply OP. We will see some implications which actually illustrate this. For the moment, these two fuzzy implications on your screen, which are the Rescher and the Fodor implication, both of them have the ordering property. Jaeger clearly does not have the ordering property. Weber also does not have the ordering property, but Weber has the identity principle. That means at x is equal to y, it is actually equal to 1. It does not have the ordering property because outside of diagonal where x is greater than y, even there it takes the value 1. Klindins does not have the ordering property, so does this particular implication. Gauguin implication has the ordering property, and so does the Łukasiewicz implication. When we introduce Łukasiewicz implication as perhaps the first fuzzy implication in the previous lecture, we have shown two equivalent ways of writing it. Now that should become clear from the geometry here. So you could write this fuzzy implication also this way. That when x is less than or equal to y, it is 1 in this region, and outside of it, it is 1 minus x plus y. Okay. So what is interesting is, let's do a small recap here. Look at this. We got these two properties from the boundary conditions and that of monotonicity, that is insisted on a fuzzy implication. It told us how any fuzzy implication will look like on the left and the right boundaries. They have to essentially be 1. This is mandatory. Now what we have seen now is, what could it look like on the right boundary and what is desirable? So that means on this line, how should it look like? Of course, it could look like I of 1 comma y is y, the identity function. It could look like 1 comma y is y square. but we wanted to investigate how would it look like on the right one. If it were the identity function, then we see that it has some nice properties. The fuzzy implication has nice properties contextually where you want to use, and that's what we have abstracted as a neutrality property. And similarly, if you're considering the bottom boundary, then we saw that it actually leads to a negation, a fuzzy negation. Once again, it could be 1 minus x or some such graph, or even a discontinuous function. Now, finally, what we have seen is, other than these boundaries, we have also seen the ordering property, the identity principle. It is related to what happens above this main diagonal, which is x is equal to y. From purely geometric perspective, this is what we have seen and abstracted, and these can also be looked at as some algebraic property, because left neutrality and the right, it's not an annihilator, but you can look at it as an inverter. And what happens when both the arguments are same? In the case of T-norms, as you said, we insist on idempotence x star x is x, whereas here we are saying that xn plus x should be equal to 1. A few further desirable properties that we expect from fuzzy implications are these. First of them is continuity. Clearly, when you look at this, Lukasiewicz implication is continuous. Gauguin is almost continuous, except at the point 0, 0, where it is 1, rest of the places it is continuous. Rescher is not continuous, Fodor is not continuous, Jager definitely is not continuous, so is Weber. Once again, we had said that in the axiomatic definition, we did not insist on many algebraic properties, but we have already seen a few. It is clear that we cannot have symmetry because of mixed monotonicity. It is decreasing in the first variable and increasing in the second variable. But what about associativity? Well, this exchange principle is some kind of an associativity. In fact, it almost plays the role of associativity in the case when you consider it in terms of implications. And why do we make this comment? That would become clear as we go forward and look at some algebraic properties that fuzzy implications can have, and also in an applicational context. So what's the exchange principle? We say a fuzzy implication satisfies the exchange principle if it satisfies this equation for any xyz coming from 0. So I of x comma I y z should be equal to I of y comma I of z. So why is it called the exchange principle? Obvious. We are able to exchange these two arguments. So keeping z fixed, if you can swap x and y, exchange them, we call it the exchange principle. Now, just like in the case of associativity, it is little difficult to give a geometric idea of it, a perspective of what an exchange principle is. So we take recourse to actually taking the formula and checking it. For instance, if you look at these 6 basic fuzzy implications, except for Rescher implication, it can be shown that all the others do satisfy the exchange principle. Now, if you look at entire 9 basic fuzzy implications and the properties that we have discussed so far, the neutrality property, exchange principle, identity principle, ordering property, and also continuity, this is how it looks like. So if you look at exchange principle, almost all the basic fuzzy implications do satisfy them. But there is not one property that all of them satisfy. So neutrality is not satisfied by Rescher, exchange principle not satisfied by Rescher. For identity principle, there are many fuzzy implications that do not satisfy. So it's the case with if it does not satisfy IP, clearly it cannot satisfy OP also. And there are also very few basic fuzzy implications which are in fact continuous. So you see here, non-continuous fuzzy implications, we have somehow presented them as basic fuzzy implication, which tells you that in spite of not being continuous, they play a vital role when it comes to looking at using fuzzy implications in a particular context. And let's talk about the contraposition principle. Once again, let's go back to this conditional statement. If f is differentiable, then f is continuous. We can ask the question, what is the contraposition of the above statement? So we know that you can look at it as P implies Q. So the contraposition is nothing but negation Q implies negation Q. So in this particular context, the contrapositive statement of the above conditional statement is nothing but if f is not continuous, then f is not differentiable. So essentially, we see that P implies Q is true if and only if negation Q implies negation P is true. So this is how you could equivalently express it in the case of classical implication. And now this is what we want to carry to that of fuzzy implication. How does this translate in the case of fuzzy implication? So we start with an implication N and then fuzzy negation N, and we say that it satisfies the contrapositive symmetry with respect to a negation N. We will denote it as Cp of N if this equality is satisfied. Clearly, I of xy is equal to I of ny, nx. Now, the question is, given an implication, how do we know whether it satisfies contrapositive symmetry with respect to any negation, some negation? For instance, let's consider these three fuzzy implications. We can ask the question, does the Lukasiewicz implication, this formula looks like this, does it satisfy contrapositive symmetry with respect to some n? Let's consider the n to be 1 minus x. So what we want is, let's look at what is ILK of NC of y, NC of x. It's nothing but ILK of 1 minus y, 1 minus x. From the above formula, we see that this can be written as minimum of 1, 1 minus y plus 1 minus x. So it turns out to be minimum of 1, 1 minus x plus y, which is nothing but ILK of x, y. So now we see that the Lukasiewicz implication does in fact satisfy contrapositive symmetry with respect to the classical negation 1 minus x. But the question is, how do we know, given a fuzzy implication, whether it satisfies the Cp with respect to any n at all? For instance, let's do the same with the Gödel implication. So the Gödel implication is 1 if x is less than or equal to y, and y if x is greater than y. So let's take the same 1 minus x. Consider what is 1 minus y, 1 minus x. This is 1 if 1 minus y is less than or equal to 1 minus x. And the second argument, if 1 minus y is greater than 1 minus x. Clearly, it could be written as 1 if x is less than or equal to y, and 1 minus x if x greater than y. So we see that this is not equal to IGD of x, y. So what we have shown now is that Gödel implication does not satisfy contrapositive symmetry with respect to the classical negation 1 minus x. But perhaps there is some other negation with respect to which it does satisfy the contrapositive symmetry. Can we say no, there does not exist any negation with respect to which it satisfies contrapositive symmetry? Or if we say there does exist, how do we say that? And if there does exist a negation with respect to which it satisfies Cp, how do we find that out? Let's look at some useful results. There is a result which says that if an implication satisfies neutrality property and contrapositive symmetry with respect to some n, then that n has to be actually the natural negation obtained from it, and it has to be involutive. So this is the result. We will not try to prove it, but I'll give you a reference where you can find the corresponding proof. For the moment, just to save space and to highlight the important aspects of the result, let's decode this result or rewrite this result in this form. If an I has NP plus Cp of n, that is neutrality property and contrapositive symmetry with respect to some n, we see that It means, it implies that n has to be equal to its natural negation and it has to be involutive. Another result says that if an implication has neutrality property and its corresponding natural negation is not involutive, then we have a much stronger result which says that I does not satisfy contrapositive symmetry with respect to any negation n. Now, if you take the Gödel implication, we know that it satisfies neutrality property. When x is equal to 1, it is y. However, what happens to its natural negation? We know its natural negation is in fact the least negation. That is, it takes the value 1 at 0 and everywhere else it is 0, which is essentially not an involutive negation. N of x is not equal to x. It immediately tells you that the Gödel implication will not satisfy contrapositive symmetry with respect to any fuzzy negation. That's the power of this result. Okay, so this is a nice result, but in some sense it has a negative connotation. It tells you when an I cannot or does not have contrapositive symmetry with respect to any negation. Is there more like a positive result? Yes, there are many, but let me give you just one. If a fuzzy implication satisfies this EP, which is the exchange principle, and if the corresponding natural negation, the natural negation that you obtain from it, if it is involutive, then what we do know is it will also satisfy NP, but most importantly, in this context, we can say that it satisfies contrapositive symmetry with respect to its own natural negation. So that's quite interesting, and that's how we found that the Łukasiewicz implication, which satisfies exchange principle, if you look at it, its natural negation is in fact the usual negation 1 minus x, and which is involutive, and we see that immediately it will satisfy contrapositive symmetry with respect to its natural negation, which is 1 minus x, and that's how we actually picked up that negation 1 minus x to illustrate this fact with the Łukasiewicz implication. You could do the same also with Reichenbach implication. You would see that it satisfies contrapositive symmetry with respect to 1 minus x. Okay, a quick recap of what we have dealt with in this lecture, or so far. We have actually axiomatized the definition of fuzzy implications. In the last lecture, we saw some geometric perspectives, and not just one. In the last lecture, we carried that forward to this lecture also, looking at how a fuzzy implication can behave at different boundaries or also on the diagonal, and what we would prefer to have along those boundaries. In that sense, we talked about the natural negation from it, and of course, continuity is always a desirable property. But more importantly, we have seen about this neutrality, ordering principle, and exchange principle. As you have seen, that they could also be viewed as algebraic or logical properties that an implication should have, and also in terms of their geometry. Finally, where do we go from here? In the next few lectures on fuzzy implications in this week, we will look at some algebraic perspectives in terms of relationships that fuzzy implications enjoy with negation and triangular norms, which are other important fuzzy logic connectives. We will see some families of fuzzy implications, the way we construct them. And finally, we will also see some functional equations involving fuzzy logic connectives, mainly implications. We will only look at them from a theoretical perspective. A few of them, there are many of them, but a few of them in a very introductory way. But all of these will have a bearing later on when we discuss properties of the approximate reasoning schemes that we will discuss later. What next? In the next lecture, we will look at how to construct fuzzy implications. So far, we have only arbitrarily given some fuzzy implications. We have stayed true to those 9 basic fuzzy implications. We hope that these formulae are quite readily recallable by you. In the next lecture, we will look at a very systematic way of constructing fuzzy implications. There are many ways. We will at least see a couple of them. Finally, a good resource for what has been covered in this lecture also is this book on fuzzy implications. Thank you once again that you could join for this lecture, and hope to see you soon in the next lecture. Thank you again.